In 2017, the Earth encountered a very weird object. We didn't know it at the time, but our planet had
There are moments in the history of science when a single discovery forces humanity to completely revise its understanding of a universe it inhabits. The moment Galileo pointed his telescope at Jupiter and saw moons orbiting another planet, the Earth-centered model of the cosmos began its slow collapse. The moment Edwin Hubble measured the distance to what had been called the Andromeda Nebula and realized it was an entirely separate galaxy, the universe expanded overnight from a single island of stars to something almost incomprehensibly vast. The moment the cosmic microwave background radiation was detected, the Big Bang stopped being a theory and became an observable fact. We may be living through another one of those moments right now, and most people have not fully registered it yet. Over the course of 8 years, between 2017 and 2025, our solar system has been visited by 3 objects that did not originate here. 3 travelers from the void between the stars, from other solar systems, other regions of the galaxy, other chapters of cosmic history that predate our sun, our planet, and everything on it. The first one caught us by surprise and raised questions we still cannot fully answer. The second one arrived and behaved with reassuring normality. The third one is the most extraordinary of all, and we are watching it happen in real time. These objects are not just astronomical curiosities. They are the first direct physical contact between our solar system and the universe beyond it. They carry information encoded in their chemistry, their structure, their behavior, and their trajectories that no telescope observation from Earth could ever provide. And the story they are beginning to tell about what the galaxy contains, how planetary systems form and are destroyed, and what moves through the darkness between the stars, is one that will fundamentally change how we understand our place in the cosmos. This is the story of the 3 interstellar visitors, and why the last one changes everything. For most of the history of astronomy, the space between star systems was considered effectively empty, not literally devoid of matter. Astronomers knew that a thin dispersal of gas and dust filled interstellar space, but empty in the sense of being featureless, uniform, and uninteresting. The dramatic events of the universe happen inside stellar systems or in extreme environments around black holes and neutron stars. The vast corridors between those systems were just corridors, transit routes connecting interesting places rather than interesting places in themselves. That assumption was built on a lack of evidence rather than positive knowledge. We had never actually sampled anything from interstellar space. We had never directly measured material that fills the gaps between stars. Everything we thought we knew about that environment was inferred from spectroscopic observations taken at enormous distances, filtered through the distorting effects of the interstellar medium itself, and interpreted through theoretical models that, by definition, had never been tested against actual samples. Our own solar system has produced objects that have been ejected into interstellar space. The mechanics of planetary formation and gravitational interaction guarantee this. When a solar system forms, not everything ends up neatly incorporated into planets and moons. Objects get flung outward on hyperbolic trajectories that carry them out of their home system and into the interstellar void. If our solar system does this, it stands to reason that every other solar system does it too. The galaxy should, in principle, be full of objects that originated in other stellar systems and have been traveling through interstellar space for millions or billions of years. The problem was that detecting them required a combination of survey technology and sheer observational coverage that humanity did not possess until relatively recently. An object moving through interstellar space is dark, cold, and small. Seeing it all requires either catching it close to a star where reflected light makes it briefly visible, or having survey systems powerful and comprehensive enough to catch fast-moving objects against the background of the sky. By the early 21st century, we were finally approaching the threshold of having both. What we found when we crossed that threshold surprised everyone who had been waiting for it. The first interstellar object ever detected arrived in our solar system in 2017, and it arrived on its own terms, which is to say, on terms that made very little conventional sense and have occupied the attention of planetary scientists ever since. The object was discovered by a telescope at the Haleakala Observatory in Hawaii and given the Hawaiian name Oumuamua, which translates roughly as the first distant messenger or scout, a name that turned out to be more appropriate than anyone realized at the time of its selection. By the time astronomers had confirmed its identity and understood what they were looking at, Oumuamua had already completed its closest approach to the sun and was accelerating out of the solar system. The entire opportunity to observe it at close range lasted only a matter of weeks. The first thing that identified Oumuamua as interstellar was its velocity. Everything in our solar system orbits the sun because the sun's gravity holds it in a closed orbit. An object can escape that gravitational hold, but only by exceeding a specific speed threshold. The escape velocity, which at Earth's distance from the sun is approximately 42 kilometers per second. Oumuamua was moving at 87 kilometers per second when first detected, already well beyond Earth's orbital distance, and clearly not in any kind of orbit around the sun. It was simply passing through, following what astronomers call a hyperbolic trajectory, a path that entered our solar system, looped around the sun, and continued outward without ever being captured. The velocity was extraordinary, but not impossible to explain. What was impossible to explain, at least within the framework of conventional physics applied to conventional objects, was what happened next. As Oumuamua moved away from the sun, it accelerated, not slightly, measurably, significantly, and in a way that could not be accounted for by gravitational forces alone. When a comet passes close to the sun, it can experience a similar non-gravitational acceleration through a process called outgassing. The sun's heat vaporizes volatile materials on the comet's surface, and the jets of escaping gas act like small rocket engines, pushing the comet in ways that pure gravity would not predict. This is well understood, well documented, and has been observed in hundreds of comets. The problem with applying this explanation to Oumuamua was that Oumuamua showed absolutely none of the visual signatures of outgassing. No coma, no tail, no detectable jets of material escaping from the surface. It was visually inert, and yet it was accelerating as if something was pushing it. The shape of the object added another layer of strangeness. Observations of how Oumuamua's brightness varied as it tumbled through space indicated that it was not spherical or even roughly rounded like most solar system objects. The brightness variation was too extreme and too regular to be explained by a roughly compact shape. The object appeared to be dramatically elongated, perhaps 10 times longer than it was wide, roughly cigar-shaped, or alternatively very flat and thin, like a disc or a pancake. Neither of these shapes corresponds to anything typical in our solar system's catalog of asteroids and comets. The combination of anomalous acceleration without visible outgassing and an extreme shape unlike any known natural object generated the most uninhibited scientific discussion in recent memory. Mainstream explanations range from a fragment of frozen nitrogen, essentially a chip off something like Pluto from a distant star system, whose nitrogen ice could generate the observed acceleration through sublimation while being essentially invisible to our instruments, to more exotic proposals involving pressure from sunlight acting on an extremely thin, flat object, perhaps a natural hydrogen iceberg. At the less conventional end of the scientific spectrum, the possibility that Oumuamua was an artifact of an extraterrestrial technological civilization was raised by serious researchers and could not be rigorously excluded by the available evidence. The honest answer is that we do not know what Oumuamua was. We observed it for weeks, gathered what data we could, and watched it disappear back into the interstellar void, carrying its secrets with it. It left behind a question that science has been unable to definitively answer, and a profound reminder that the universe is under no obligation conform to our expectations. 2 years after Oumuamua left the solar system and the scientific community was still debating its nature, a second interstellar object appeared. This one was discovered by a Crimean amateur astronomer named Gennady Borisov in 2019, and it was given his name. Borisov arrived from the direction of the constellation Cassiopeia, a different region of the sky from Oumuamua's origin point, indicating a different origin in the galaxy, and it too was traveling on a clear hyperbolic trajectory. But the similarities with Oumuamua largely ended there. Borisov looked like a comet. It had a coma. It developed a tail. The gases sublimating from its surface as it approached the sun were measurable and identifiable. Its chemical composition, the mix of volatile compounds detected in its outgassing, was broadly consistent with the composition of comets from our own solar system, though with some differences in the relative proportions of certain molecules that hinted at formation conditions slightly different from those that produced our local comets. It tumbled through space in the shape of a reasonably compact nucleus, consistent with what we would expect from any icy body that had been drifting through cold interstellar space for millions of years. In short, Borisov was recognizable. It was interstellar. The hyperbolic trajectory was unambiguous, but it was a kind of interstellar object that the theoretical frameworks for planet formation had predicted should exist. A comet ejected from its home system during the chaotic early phases of planetary formation, set adrift in the galaxy, and eventually intercepted by our sun's gravity for a brief encounter before continuing on its journey. If Oumuamua had raised questions, Borisov offered a degree of reassurance. The universe contained objects that behaved according to known physical principles, even when they came from somewhere else entirely. The lesson of Borisov was that not every interstellar visitor would be a mystery. Some of them would simply be comets, alien comets, formed around other stars, chemically enriched by different conditions, but fundamentally recognizable members of a class of objects we already understood. This turned out to be valuable context for understanding what came next. On July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System, a network of automated sky survey telescopes distributed across Hawaii, Chile, and South Africa, detected a moving object and flagged it for follow-up analysis. Initial examination suggested a new asteroid, a routine discovery of the kind the survey system makes regularly. Then the velocity measurement came back, and everything changed. The object was moving at approximately 58 kilometers per second at a distance of 4.5 astronomical units from the Sun, just inside Jupiter's orbital distance. That velocity at that distance was unambiguously hyperbolic. Another interstellar visitor had arrived. It was designated 3I Atlas, the third interstellar object, and within days of its confirmation, it was clear that this one was in a different category from either of its predecessors. The size of 3I Atlas is the first thing that sets it apart. Oumuamua was estimated to be a few hundred meters in its longest dimension, a small object by any astronomical standard. Borisov's nucleus was approximately 1 kilometer across. 3I Atlas appears to have a nucleus that could be as large as 10 to 11 kilometers in diameter. This is not a marginal size increase. It is an object potentially 10 times the mass of Oumuamua, 5 times the mass of Borisov, the largest interstellar object ever detected by an enormous margin. The direction it came from is equally significant. Oumuamua and Borisov both arrived from the general direction of the northern sky, broadly consistent with the direction our solar system is moving through the galaxy. In a sense, those objects in our solar system met head-on. We were moving toward them at the same time they were moving toward us. 3I Atlas arrived from a completely different direction, hitting the solar system from the side in what astronomers have described as a T-bone collision geometry. This means it genuinely originated in a different region of the galaxy from either of its predecessors, and trajectory analysis points toward the thick disk, the older, less chemically enriched outer layer of the Milky Way above and below the thin disk where most stars, including our sun, reside. Objects in the thick disk are old, very old. The estimated age of 3I Atlas based on its trajectory and its probable origin in the thick disk is potentially over 7 billion years, older than our own sun, older than Earth, older than every planet in our solar system. If those estimates are correct, 3I Atlas formed before our solar system existed, has been traveling through interstellar space for longer than the Earth has been a planet, and has encountered 93 other star systems along the way without coming close enough to any of them to be captured. Until now, the chemistry of 3I Atlas has confirmed that it is a comet. It has developed a coma and exhibits outgassing as it approaches the sun, but a comet whose chemical composition departs from solar system norms in striking ways. Its early outgassing was dominated by carbon dioxide rather than water vapor, a ratio almost completely inverted from what we observe in comets from our own solar system. This explains why the coma formed unusually early, at distances from the sun where water ice is still frozen solid, and it points toward formation conditions in which the relative abundances of volatile compounds were significantly different from those in our own solar system's formation environment. 3I Atlas is not just an old object from a distant region of the galaxy. It is chemically distinct from everything in our immediate cosmic neighborhood, a physical sample of conditions that existed somewhere else in the Milky Way over 7 billion years ago. One of the most remarkable aspects of 3I Atlas's passage through our solar system is the trajectory it follows on its way through. Unlike Oumuamua, which passed through the inner solar system quickly and at angles that kept it away from most of the planets, 3I Atlas is conducting something close to a comprehensive tour of the solar system's major bodies. Its closest planetary encounter is with Mars, passing within approximately 28 million kilometers, close enough that instruments in Mars' orbit and on the Martian surface have been turned toward it, providing observations from a perspective that no Earth-based telescope can replicate. Its trajectory then brings it into proximity with Venus before it arcs back outward past Jupiter on its way out of the solar system. 3 separate planets, 3 separate observational opportunities, 3 different sets of instruments gathering data on the same object from different vantage points simultaneously. This observational richness matters enormously for the science. The data returned from each encounter adds a different dimension to our understanding of the object, its size, shape, rotational state, chemical composition, outgassing behavior, and how those properties evolve as it moves through different temperature and radiation environments during its solar passage. The trajectory also passes 3I Atlas behind the Sun from Earth's perspective during October and November, creating a period of weeks during which direct observation from Earth is impossible. When it reemerges in December, the Sun will have done its work, heating the surface, driving sublimation at its maximum rate, potentially altering the surface in ways that are observable and informative. The post-perihelion 3I Atlas will be physically different from the pre-perihelion version we've been studying, and comparing the two states will tell us things about how interstellar objects respond to stellar heating that no theoretical model could predict with confidence. There is also the possibility, unlikely but real, of direct spacecraft observation. The Juno spacecraft, which has been studying Jupiter and its moons from orbit for nearly a decade, is within range of 3I Atlas's trajectory during the outbound leg of its solar passage. A mission extension or orbital adjustment that brought Juno into close proximity with 3I Atlas would be among the most scientifically valuable maneuvers in the history of robotic space exploration. The opportunity to photograph, spectrally analyze, and potentially directly sample the environment of an object from another star system with a spacecraft already in the vicinity. Whether that opportunity is realized depends on factors ranging from spacecraft fuel reserves to institutional priorities to political will. But the possibility exists in a way that it never did for Oumuamua or Borisov, and the scientific community is acutely aware of it. The fact that humanity detected 0 interstellar objects across all the centuries of astronomical observation that preceded 2017, and has now detected 3 in the space of 8 years, is not a coincidence. It is a consequence of the dramatic improvement in our survey capabilities during that period. The automated sky survey systems that now cover the entire accessible sky on regular cadences are finding things that were always there, but that earlier generations of telescopes lacked the coverage and sensitivity to detect. This means that the 3 objects we have found are not rare visitors who happen to arrive during a special period in human history. They are representatives of a continuous and substantial population of interstellar objects moving through our solar system at all times. Theoretical estimates based on the detection rate suggest that there may be thousands of interstellar objects within our solar system at any given moment, most of them too small or too distant to currently detect, but real nonetheless. This population constitutes a sample library of the galaxy's planetary systems. Every interstellar object carries chemical and physical information about the stellar system where it formed, the conditions that produced it, and the journey it has made to the galaxy since its ejection. Each detection is not just an encounter with a single unusual object. It is an opportunity to read one page of a library that encodes the history of planetary formation across thousands of star systems distributed across billions of years of galactic history. We have now read 3 pages. Oumuamua showed us that the galaxy contains objects that break our physical expectations in ways we cannot yet fully explain. Borisov showed us that it also contains objects consistent with our models, alien but familiar, different but recognizable. And 3I Atlas is showing us something more profound than either, that the objects moving between stars can carry the chemical signatures of conditions that existed in the early galaxy, before our solar system was born, in regions of the Milky Way that we can observe with telescopes but have never touched with instruments. Until now, before 2017, the solar system was in a meaningful sense self-contained. Everything in it came from here. Everything we could study directly had formed in the same cloud of gas and dust that produced the sun. The boundary at the heliopause was the edge of our accessible world. Anything beyond it was observable only from a distance, filtered through the limitations of remote sensing. 3I Atlas and its predecessors have changed that. The boundary has been crossed, not by us going out, but by the galaxy coming in. Objects formed around other stars in other conditions at other times in cosmic history are arriving in our solar system carrying physical samples of realities we could not otherwise access. We can study them. We can measure them. We can learn from them things that no telescope pointed outward could ever tell us. The view of space that these three visitors enable is fundamentally different from the one that preceded their arrival. The solar system is no longer an island. It is a waypoint, a place where the traffic of the galaxy occasionally pauses long enough to be observed and interrogated. The universe beyond our sun is no longer an abstraction accessible only through light. It is beginning, slowly and incrementally, to make itself directly known. 3I Atlas is the most extraordinary of these messengers yet. Ancient, chemically alien, enormous, and arriving at a moment when our instruments are finally sophisticated enough to do it justice. Whatever we learn from it in the months and years ahead will add to a picture of the cosmos that is already unrecognizable from the one we held before the first distant messenger arrived. The view of space will never be the same again, and that is exactly as it should be.